with the 6.6 Schrödinger wave equation. In previous section, we discussed a physical state through a given wave function, from which we could draw any information of the system by applying an eigenvalue equation, normalizing the wave function and calculating the corresponding exception value. There is no need to specify the function if it was a space and the time depend on a spatial function only. Now, it is time to ask for the detail of the wave function, as the detailed wave function is used to govern an equation that captures the essence of the dynamic of microscopic particles through wave mechanics approach. This approach is derived from an energy eigenvalue equation and hence an operator for the total energy. The Hamilton operator is given. The governing equation is in the form of the second-order partial differential equation and is known as Schrödinger equation. Once developed, it is solved to describe the dynamic of the system. The following sections are thus devoted to solving the Schrödinger equation for a variety of given physical system with no potential or simple form of potential applied. Therefore, developing the governing equation used to describe the dynamic of microscopic particles are as follows. Firstly, we rewrite a symbol for a one-dimensional wave function c when x point t and spread it into spatial and temporal components as follows. Secondly, we write the Hamilton operator for total energy as Hamilton equal to K plus V. This is potential, where K blah 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 is the kinetic energy operator and V is potential energy operator assumed to be independent of time t and hence V is the function of space only. This is useful for deriving time-independent eigenstates C, X. These states are of great interest in most cases of one-dimensional potential problems and will be determined for various physical situations as shown below. Okay, let's start with En is the eigenvalue of Hamiltonian, providing the possible value of total energy of the system, and Vn is the eigenfunction for stationary state. The subscript in n in both n En and Vn is refer to a particle solution represented by one of these states. Thus, there are different stationary states represented by different stationary wave function for each allowed level of energy. Below are some interesting points regarding both V, St and Vx in quantum mechanics. We here, along with 7.7, show that the probability density of this does not depend upon time. Okay, so the probability density and expectation value are constant in time. Hence, we might expect that in any measurement of a physical quantity, the constant value is obtained. But 7.11 and 7.12 show that no matter whether we use Vxt or Vx for quantum measurement. Now, we'll start in 6.7, dynamic of a free particle. Suppose a particle of mass m confined to an infinite square well of which along the x-axis, see figure 7.1, with the surrounding potential given by V. This is V equal to 0 and 0 and x is less than 0, less than a, less than equal a. Such a trapped particle inside the infinite well is then said to be completely free, having only kinetic energy. A similar situation in a classical model would be an object moving back in forth of a frictionless surface bounded by rigid walls. In both cases, there is no way out for particles to go through the walls. Thus, outside the well, Vx equals 0, and hence the dynamic is applied only to the region inside the well, where Vx equal to 0. Therefore, the time-independent Schrödinger equation inside the well is blah blah blah. Okay. In which case, we provide to be depend upon positive integer number n. Since the dependence of energy of the total kinetic of total energy A on K is clear from 7.70. Total energy is a particle in an infinite square where potential is quantified. It follows that the magnitude of A is determined by n, as seen below. Thus, the above the above equation provides the eigenvalue of energy. That's possible. A Lorentz value of total energy for the particle inside the infinite square well are equally important. The free particle. It is clear that total energy increases proportionally to n squared, and that is A2 equal to 4 times A1 and A3 equal to 9 times A1, where A1 is the lowest energy, see figure 7.2. Okay, although we have already found the eigenenergy for the particle inside the well, we have not determined especially the eigenstates C and. The first thing to do is to fix the constant A through the normalization procedure. Okay, here we only pick the starting procedure and resulting constant as follows.